Okay, so my name is Jennifer Lowe, and I'm going to be talking about multi-precision GMRES in Trilinos. This is joint work with Christian Gluza, Eric Bowman, Ichi Yamazaki, and Siva Rajamanikam, all from Sandia National Labs. So the previous two speakers have given you a great introduction to GMRES with iterative refinement and why you might want to use lower precisions in Krylov solvers. So just to recap that again, Krylov solvers are typically memory bound, so using lower precision, and in my case that means I'm going to try to incorporate float precision instead of double precision, can reduce the cost and time of data movement. Floating point operations are cheaper for the computer. And we want to take advantage of the new hardware, such as the NVIDIA Tensor Cores, maybe in the future, that Azam was talking about, and other hardwares that are being made to specifically speed up low precision computations. But the challenges for this are that lower precision computations still result in more round-off error in your computations, and that applications, specifically the sorts of PDEs and modeling that we do at Sandia, these applications still need a very high level of accuracy in their solutions. Okay, so a little bit about the Trilinos infrastructure and the software that I'm working on. I'm working on Belos, which is the linear solvers package in Trilinos. And all of the linear algebra kernels in Belos are abstracted through this adapter interface. So there's no linear algebra in Belos itself. You interface to whatever linear algebra software you want to use. All of the Belos solvers are templated upon a single scalar type, but unfortunately this solver's interface does not support mixing precisions. So any mixed precision must occur through the adapter. So my work has been using Kokkos and Kokkos kernels, which are libraries for portable parallel linear algebra, specifically on GPUs, which is what we're interested in testing. And I've written an adapter to use Kokkos as the linear algebra backend for Belos solvers. And we're able to implement mixed precision operations via this adapter. And this has allowed us to test performance improvements to GMRES in mixed precision on a single node with GPU. And eventually we hope to expand this to multiple nodes, maybe to T-Petra, and make these mixed precision solvers available to applications using Trilinos. So Bastian and Azam both gave an excellent introduction to the history of GMRES with iterative refinement. I'm using a different variation on the algorithm than either one of them was using. So when I talk about GMRES IR, I'm talking about an iterative refinement with only GMRES for the error correction. We decided that since we're testing on GPUs with very large matrices, we wanted to avoid any sort of ILU or LU preconditioning because the sequential nature of triangular solves makes them less performant on GPUs. So we wanted to stick with parallelizable preconditioners. So for my iterative refinement with GMRES, I'm computing the residuals in double precision. I'm updating the solution in double precision. And then in between, I'm doing an error correction with GMRES, no preconditioning of any kind right here. Later, I'll talk about a polynomial preconditioner that we add to this, but no LU preconditioning whatsoever. So this is the algorithm I'm using in Trilinos. And what's interesting is to look at the convergence here. So I'm using GMRES 50. So restarting GMRES every 50 iterations. And I compare double precision GMRES, a single precision only GMRES just for the sake of comparison. And then with my GMRES IR, I'm recomputing those residuals in double precision at each restart. So I run GMRES in single precision for 50 iterations, and then I recompute my residuals and my solution update in double precision after those 50 iterations are over. And then I rerun GMRES, restart GMRES, and run in single precision for another 50 iterations. So this particular matrix is a 2D convection diffusion problem over a 5-point stencil. Its size is 2.25 million, has about 11 million non-zero elements. I'm running to a relative residual tolerance of 10 to the negative 10. And these tests are run on a V100 GPU. So what's interesting here is that since we're restarting frequently enough, you can see GMRES IR convergence very closely follows the double precision solver convergence. It takes a few more iterations for the GMRES IR solver to converge, but since they're converging in a similar number of iterations, we get a significant speed up from the GMRES IR solver. So the double precision solver to run to convergence takes about 50 seconds, and the GMRES IR solver takes about 30 seconds. And if we break this down into specific kernels, so here's the kernel speedup for the problem I just showed you. In the bar graph, again on the left, you have the double precision solver that took about 50 seconds. On the right, you have the GMRES iterative refinement solver that took about 38 seconds. And you can see I've split this up into kernels. So most of the solve time is in the orthogonalization kernels, which consist of the two GMVs and the norm. And then the rest of the kernel is split up into this sparse matrix vector product in the purple. And these other operations in the top for the double precision solver, that's just your small dense operations solving the least squares problem. For the IR solver, that also includes recomputing your residuals and your new solution in double precision. So it's interesting to look at the speed up in each of these kernels. Of course, with the total speed up from 50 seconds to 38 seconds, that's about a 32% speed up to run this GMRES IR solver to convergence, mostly using single precision operations. The GMV with a transpose gets about 28% speed up. The GMV with no transpose is better, gets about 57% speed up. Norms are fairly negligible. Our sparse matrix vector product is interestingly getting almost 2.5 times speed up. And we've seen this with several other examples. So this is something we need to look more at. Why is this sparse matvec getting such a great speed up? And this, by the way, is all using classical Gram-Schmidt orthogonalization, 2 steps of CGS to CGS. And this graph just shows that we get similar kernel speedups with some other problems. So the blue bar is the convection diffusion problem that I just showed you. I also include a Laplacian, and then in the green is a different convection diffusion problem. And these problems are of different sizes, ranging from 1 million to 6 million. And we do get similar speedups in all the kernels for these 3 different PDE problems. Now, one question that's interesting when you're running GMRES as your error correction is, how do we choose the best restart size to get a good speedup in our GMRES problem? So this is back to the convection diffusion problem that I showed at first. And the first example that I showed you was with a subspace size of 50. And now I tested larger subspace sizes. So I'm restarting both the GMRES double and the GMRES IR at the same point. And at each restart, I recompute the residuals and the solution in double precision for GMRES IR. And for this problem, it's interesting that even though in the double precision, the larger subspace size gives you fewer iterations, this problem is so dominated by the dense matrix operations that are required for the orthogonalization that as you build out a larger subspace, these orthogonalization operations dominate the solve time. And actually, the smaller subspace size of 50 gives you the cheapest solve time here. And this is a very difficult problem, requires many iterations to converge. But in any case, across all of these subspace sizes, we're still getting improvement with the GMRES IR solver. We're having a slight increase in the number of iterations needed for convergence, but we're still getting improvement of 20 to 44% in our total speed time using this GMRES IR scheme. Now, unfortunately, this isn't universally true. You can choose too large of a restart size and cause yourself problems. So these are timings for a 3D Laplacian, which is fairly large. But this problem, we don't get speed up from the GMRES IR solver for really large subspaces. So for this graph, I have on the x-axis different subspace sizes. And for each subspace size, the bar on the left indicates the solve time for the double precision solver, and the bar on the right indicates the solve time for the iterative refinement solver for each of those subspace sizes. And again, these are broken down into different kernels. So for each subspace size, we get good improvement with the GMRES IR solver up to about subspace size 150. But then when you increase the subspace size to 200, 300, and 400, the GMRES IR solver is no longer restarting frequently enough. It's no longer getting that residual correction in double precision frequently enough to keep up with the double precision solver in Convergence. So at subspace size 300 and 400, the iterative refinement solver needs many more iterations to converge than the double precision solver. And in that case, it doesn't give us much speed up. However, for the much larger problems that we want to run in applications, those problems with GMRES will probably need a smaller subspace size. And so we aren't as concerned that we don't get speed up with these larger subspaces, because we'll mostly be using smaller ones in practice. Okay, finally, some preconditioning. So I've added a polynomial preconditioner to our GMRES with iterative refinement. And this polynomial preconditioner is both computed and applied in single precision during the GMRES single precision solve. This is the same polynomial preconditioner that Ron Morgan talked about several talks ago. We've implemented it into the Belos linear solvers library. This particular problem is on a Laplacian with a stretched grid, but of course you could use it with any non-symmetric matrix as well. And we're still using a convergence tolerance of 10 to the negative 10. And the nice thing here is that, again, we get improvement using the GMRES with iterative refinement over several different degrees of the polynomial preconditioner. So again, here on the x-axis of this graph, I have several different polynomial degrees. The bar on the left is for the solve time for double precision. The bar on the right is the solve time with this iterative refinement solver. And these bars are split up a bit differently as far as breaking down the solve time. So I have the orthogonalization kernel at the bottom in blue. The matrix vector products are in orange. And all of the remaining operations are at the top in the gray. So with polynomial preconditioning, remember the previous problems that I showed were dominated by orthogonalization costs, by those GMVs with the transposes and non-transposes for the orthogonalization. Using polynomial preconditioning shifts the balance of the solve time to the sparse matrix vector product. Included in those other operations at the top are the vector additions for the polynomial preconditioner. So we still get a good improvement from polynomial preconditioning itself. So with the degree 10 polynomial, our double precision solver needs about 3,000 iterations to converge. And using a degree 60 polynomial, the double precision solver needs about 297 iterations to converge. So the polynomial preconditioner itself gives us a great improvement. And we're still getting good improvement with our iterative refinement solver as far as the solve time. We get improvements in solve times of about 33% with this iterative refinement solver over the double precision solver. So the nice thing here is that we've shifted the balance to the sparse matrix vector product instead of the orthogonalization, which in some cases may be advantageous. Okay, so conclusions. In our experiments so far with several sorts of PDE type problems, this GMRES with iterative refinement gives a reasonable performance improvement over the double precision GMRES restarted every 50 iterations. Most of these speedups are in the orthogonalization and in the sparse matrix vector product, but the impact of which kernels you speed up depends on your choice of preconditioning scheme. Again, we're incorporating this into the Trilinos library with a Kokkos backend so that it can run on GPUs. And we may eventually expand this to the tPetra library and make it available to applications using Trilinos. So in the future, we'd like to spend more time looking at the choice of restart size for GMRES and how that affects the convergence of the iterative refinement solver. We'd like to test other Krylov methods, perhaps CG or MNRES or BiCG stab. We're looking at more preconditioning options, more parallelizable preconditioners such as block Jacobi. Kokkos is building support for half precision, so we also want to test half precision in our iterative refinement solvers. And there's also work by Christian Gluza investigating some low precision multi-grid preconditioning. And that is all. Thank you very much for your time.
Thank you. Well, a few questions, and I think you've actually answered them, a few of them in this last slide. But some questions still remain. So Daniel asked, is the time savings mostly from communication savings or MATVEC times?
So I think the time savings, I mean, you're getting a lot of time savings earlier. Let me go back to this example. Quite a bit of that time savings is the dense MATVEC, but you get a good speed up in the sparse MATVEC as well. I think this is both improvement in data movement. You're not having to move as much data between registers and so on and so forth. And I mean, we're also getting speed up in the computation times as well. So
I think the question probably might have been asking both the MATVEC. I mean, you've got a dense MATVEC and a sparse MATVEC. They're both. I'm not sure which MATVEC he's referring to, but the other question. Let's see. Did you consider trying one of those mixed precision orthogonalizations?
We have considered that, and so that's a possibility for the future, but we haven't implemented that so far.
Okay. Oh, did you list that in your future work?
Not specific.
Okay. Why don't you go to that slide? Let's see. Do you have a model for basis size versus expected difficulty?
No, I don't have such a model.
I think you had a plot.
At this point, I think as far as applications go, yeah, we're just assuming that we're going to need to use a smaller GMRES basis for the size of the problem. I tried a problem a little bit larger than this, and I was getting out of memory errors with the subspace sizes of 300 and 400 on the GPU. So,
and then let's see. The last question was about the optimal restart size, and that I think is one of your future work questions.
Yes, we're looking at optimal restart size.
Okay.
Future work.
And then performance difference with CPUs and GPUs. Here, what's the performance difference?
That's a good question. I haven't been testing these problems on CPUs. They're of such a large size that we jumped straight to the GPU because that was our focus.
Okay.